All right, everybody, we're going to talk about mass wasting now. So this is a surface process that happens, um, and it can be broken down into, pun intended, into a number of different types. And yeah, let's get into it. So mass wasting is defined as any downslope movement of soil or rock. And this is under the influence directly of gravity. Okay, so just gravity pulling uh, any kind of earth materials downslope. This includes slides, so rock or debris slides, rapidly moving debris flows, slow moving creeps like soil creep, and rock falls. And go ahead and click on that link in the slides when you're studying for our second test uh, and give it a look. So here's a map sort of outlining the potential for landslides across the continental U.S. And in red, we see high potentials. In yellow and green, we got intermediate, and then those unshaded areas, kind of the majority here of the this kind of beige color here, that's low or unknown potential. And I want you to think about what lies here in this part of the U.S., what lies over here in this part of the U.S., and what lies over here. So one of the driving forces in mass wasting is the slope angle. So that's for mass wasting to occur, there has to be a slope angle, right? If there aren't any slides on flat ground. Most rapid and spectacular mass wasting events occur in areas of rugged, geologically young mountains. And this is because older mountains, most likely they've been around long enough that most of the material that is going to fail on the side of a slope has already fallen and failed and has been eroded away and transported as sediment. So here we want rugged, so high topography, and we want young mountains. And along with that, as the landscape ages, we get less dramatic downslope movements because those mountains are eroding down, and that's changing both the amount of material present to fail and fall, but also that's changing the slope angle, right? It's making it from a steeper angle when they're young to a more shallow angle when they're older. And mass wasting is a geologic process, right? And it follows weathering. So weathering is acting on the slope first, like we talked about with sedimentary rocks. Then you get slope failure. And it's a combination of mass wasting or slope failure and running water that will produce valleys like the dramatic Grand Canyon that we see over there on the right. Those are from mass wasting processes where these taller slopes up here that are higher up and steeper. Materials falling off of those, and you can see it's landing down here in these slopes here. And then that stuff eventually makes its way down into a valley where it's carried away by the Colorado River. And here's a cross section of that if you want to see kind of what's happening there. So one thing I want you to think about is that these were all sedimentary layers that went all the way across at one point, and now through mass wasting and transport, these materials get carried away, and that's how we're getting these valleys here. So what are the driving forces at work for mass wasting? And I want you to think about that. And I also want you to think about what forces resist slope movement or mass wasting. So if we look at it from a physics angle, the force that is acting on any object on the surface of the Earth is gravity. And here we've got two blocks, one on a flat surface here, and then one on a sloped surface. And gravity is always pulling straight down relative to the center of the Earth. It's pointing towards the center of the Earth. So on a flat surface, there's only the force of gravity here and then the force of gravity coming up from the flat surface, which we call the normal force here, because that's straight down to the surface that it's sitting on. And here, there's no side-to-side forces, so this block is not going to move. It's just going to sit there like a cup on a table. But as soon as you begin to slope that surface, the normal force is still pointing straight down towards the slope, like you see over here. The normal force is straight down at the surface, but the force of gravity now is pushing down towards the center of the Earth. And in physics, we have these two vectors here, and then the vector that connects them tells you what the shear component is. And that's a fancy way of saying that there's a force that wants to push the block down the slope. And weight is a function of that, is a function of gravity. So as you have more weight on the slope, that increases the influence of gravity, and that raises the chances that this block is going to want to slide. So what forces do you think might resist the force of gravity? Well, here we've got two. We've got the cohesive, or strength of the slope materials, right? So how strong is the material on the slope, right? And I want you to think, like, if you had a slope that's made out of granite, or you had a slope that's made out of sandstone, what do you think would be stronger? Well, it would be the granite, right? So this is the actual strength of the material on the slope. And then you have frictional forces that hold the slope in place. And I'll talk a little bit more about, excuse me, what types of things affect those frictional forces. So again, the controls on mass wasting is the slope angle, right? So if you have a steeper slope angle, it's more likely, mass wasting is more likely to occur. Slope material, so is it rock? Is it loose sediment? Is there water present? And then are there structural discontinuities like fractures, a boundary between two bedding planes? And bedding plane means, you know, a plane of sandstone and then limestone and then mudstone. Each of those have different strengths, and at their boundary, that'll have a different strength than inside the actual formation itself. And then is the rock cleaved at all, or is it a rock that wants to cleave? And then also vegetation. So the presence of vegetation or the lack of vegetation are also controls on mass wasting. So in addition to the controls, or the things that regulate mass wasting, like I just mentioned, let's talk about what are the potential triggers. So they are slope angle change, the addition of water, the addition of weight, the removal of vegetation, and earthquakes. And if there's no actual events that triggers it, sometimes you just get the gradual weakening of slope material through the weathering process. So for slope angle, you can imagine we're pouring dry sand out of a cup onto a table. And once you get to a certain angle here, that stuff is going to start to fall down. And if you just keep pouring, it's going to fall down, and it's going to reach an angle, and it will always stay that angle no matter how much material you add to it. As you add more material, just more sand will collect at the base. So the pile will get bigger, but this angle here between the top of the pile and the bottom will stay the same. And we call that the angle of repose. And we see that in dunes in like desert environments. We see that in dunes on Lake Michigan or anywhere else that you might find sand dunes. And the angle of repose for dry sand is a constant angle. And I usually have a lab that goes with this, but I will mention we're not going to have time to do that lab necessarily. Although if you want to do the demonstration, or want me to do the demonstration, I will. But the angle of repose for dry sand is about 32 to 35 degrees. And this can change a little bit with talus slopes, or slopes that are falling down on rocky cliff faces. And this is because some parts have little rock outcrops here, okay? And some of these weathered materials that are falling down and depositing here aren't nice round grains like this sand here. So there you can get a little bit of variance in how steep it is based on whether something is supporting, like here, this little outcrop or crag here is supporting the stuff above. So you might get a slightly steeper angle of repose than you would have down here. And also because the pieces that are deposited here are angular, sometimes you can get slightly steeper angles that way as well, because those rocks aren't going to preferentially slide past each other. And then if you have a scoria cone, same thing here. You can get different angles, but generally speaking, this scoria cone has a very similar angle of repose to sand because the grains in the scoria are maybe a little bit finer. But remember, scoria has lots of little air pockets and things in it, so sometimes those things can build up to slightly steeper angles before that stuff fails and falls down. So you can have oversteepened slopes. So this is unconsolidated particles, and they'll assume a stable slope at the angle of repose, right? And again, like I said in the last slide, this is different for different materials. But if you oversteepen a slope, they're unstable, and that can trigger mass wasting. And that the causes of the changing slope angles can be natural processes, like a stream is cutting through a slope. That can oversteepen it. People can oversteepen it. So if it's excavated to build structures or roads or mines or something like that. And here's an example of that. So here you've got somebody cut a little driveway here for their house, and then they built a house here, and they've oversteepened the slope, and it might be fine until they get a heavy rainfall, right? And also we have fill down here. That heavy rainfall is going to do something to this slope, and I'll explain what it does here in a little bit. And that could cause failure of this upper slope, and it can also cause failure of the slope further down. And what that is water. So the role of water in mass wasting is, as you saturate sediment, you reduce the friction between the materials, okay? So when sediment pores fill with water, the cohesion among the particles is destroyed. So you got to imagine when you have dry particles here, friction is what's holding these, and friction is overcome by angles in sand anyway. Friction is overcome by angles greater than 32 to 35 degrees. Once you get to above 32 or 35 degrees, that will overcome the force of friction and you'll get slope failure. However, if you add just a tiny bit of water where you just kind of dampen it, you still have pore spaces, but there's a little coating of water around each grain, and that can actually increase the cohesion, okay? And this has to do with hydrostatic friction that occurs between water molecules, basically. But once you oversaturate it to the point where the grains are no longer touching one another, then you have zero friction, and that wet sand will completely collapse, right? And also, water adds weight to the mass of the material. So, and remember, weight also causes slope failure. So what can add weight to a slope? Well, building on a slope, right? Building a structure on the top of a slope or on a slope somewhere will add weight. Heavy rainfall, like I said, will saturate the slope, and that decreases the cohesive strength, like I said, and it adds weight to the material. So what about the role of vegetation? So with vegetation, oftentimes plants can bind soil and other materials, rocky materials that we call regolith. It can bind those things together as roots go down into the soils and eventually reach the regolith, which is the rocky layer below the organic soil part. It can kind of bind all that stuff together because the roots offer some kind of structural support, sort of like I-beams in a building. And in addition, vegetation also can shield soil surface from the impact of raindrops. And so that will bind a slope together, sometimes in ways where it can overcome that angle of repose, like we talked about, that causes slope failure. But if we remove vegetation, then that binding material is no longer there, and the slope can fail. So what could cause the removal of vegetation? Well, the main ones are clearing. So here's a picture here of some cleared forest, probably for logging. And so now you have bound material up here, but then down here, you've removed the vegetation that was binding all that stuff together. Sometimes fires can come through, and that will also eventually lead to a clearing, right? But this could be naturally caused in addition to caused by humans. And then you can also have drought. If there's not enough rainfall in an area, eventually those plants will die, and there again, no longer bind the soil and regoliths together. So let's move on to how we classify different types of mass wasting. So it's based on the following criteria. So the type of material involved, so is it rock, is it debris, is it coarse-grained soil, earth, or fine-grained soil? How the material moves, that is, does it slide, does it fall, does it flow? The moisture content of the material, slides can be dry or wet, flows are wet, falls are usually dry. And then the velocity, how fast is it moving? So here's some examples. So here you have a slump, or you can have, and slump is just when one side of the slope, maybe not the entire slope, but a portion of the slope will kind of all slump down. These look like little normal faults here. And this is where a material is just sliding past itself on the way down. So it'll produce something that looks similar to this. If you've ever driven down south, like through the Southern Appalachians or the Ozark Mountains or the Blue Ridge Mountains, anywhere down there, you'll see a lot of this kind of stuff. Namely because we have a lot of vegetation down there. So when you clear things, you get a lot more chance for slump. You can have rock slides, right, where it kind of slides down in sheets like this. And you can see these are sedimentary layers here, right, that have been uplifted and folded. So they're at some kind of a dipped angle. And so material that's sitting on, let's say this is a mudstone, and then this is a sandstone above it. The sandstone will slide away, whereas the mudstone is a little bit more, there's a little bit more friction. So it's not going to all slide together. Maybe the sand is going to slide much more easily than the mud would, if it's dry anyway. And this is an example of where things slide along different sedimentary boundaries. We can have debris flows like we have in Death Valley, where debris falls down into these kind of valleys and then runs down slope. And then when it hits to the bottom here, it'll cause this kind of big fan shape, similar to what I'll talk about in the next lecture with river deltas. And then you can also have earth flow, where there's just a slight slope, but there's enough force of gravity and enough loss of friction through different processes that earth will just kind of slump down. And this is an example of almost creep, but maybe it's moving fast enough that we would call it a flow. So flows include creep, debris or mud flows, or a debris avalanche. And this is where the particles are moving relative to each other. They usually involve water, right? And the material moves downslope as a viscous liquid, right? Remember, viscous means kind of a thicker liquid, right? So, because viscosity is resistance to flow, but it flows nonetheless, almost like a liquid. And this is where you just have a lot of water and a lot of solid material mixed together that can flow almost as a liquid. So here's the different types of slope failure that involve flow. So part one, we have creep. And here's where this soil layer that's above this almost vertically dipped sedimentary layers, this is where the soil layer itself, so the earth layer on the top, is beginning to slide down slope, right? This rock isn't really flowing at all, right? It's pretty solid, but the material on the top can flow. We call that creep. And we can get stuff like this. This is out west. This is a relatively gradual, shallow slope. But when it rains, there's enough saturation of the soil that it will begin to flow preferentially. And this is a fence that was once straight across, but slowly this stuff is flowing down, and now you can see the fence is creating like the kind of this lobe here. And so that's creep, and that's real slow moving. And then you can have mud flows, and these can be much more sudden. So here's some mud flows over here. And then you can have debris flows, okay? Debris flows are where big amounts of debris, whether they be chunks of rock or soil or mud or anything, all that stuff comes down. And so at the bottom, you'd get a mixture of all different sized materials, things like that. And then you can have a rock or debris avalanche. And this is generally when a slope will fail and you get a bunch of material almost falling vertically down, okay? So these are on real steep slopes. You get these at the tops of really young mountains. And you can have rock avalanches. You can have debris avalanches, which is kind of smaller materials, plant materials, rock, snow, all of that stuff falling down. We'd call that a debris avalanche. And a really interesting way that soil can creep, and by the way, creep is really slow, like let's say millimeters per year. And that's like a continuous downhill movement of soil and rock on steep slopes. And one really interesting way that occurs is through freeze thaw, or the wetting and drying of material. So you can imagine, let's say with freeze thaw, you've got soil here. These are grains of soil or small rocks, little rounded rocks. And when water is in the soil and it expands, it pushes the material away from the slope perpendicular to the slope. So at a 90-degree angle from the slope, and that's denoted by these blue arrows here. Then come spring, when it thaws, that material falls straight down due to gravity. So that grain started here, moved 90 degrees from that slope, and then fell straight down. So you can imagine this is like the normal force pushing up, and then the force of gravity pulling it back down. So this grain was here, now it's here. Then it moves up here and comes down, now it's here. And over time, you can get this cascading effect where now that grain's all the way down here, right? With debris flows, generally this is dense, fluid mixtures of rock, sand, mud, and water. Mostly debris flows are mud or mud flows, or in the case of volcanic debris flow, you can get a lahar, which is like a superheated debris flow. It's generated during heavy rainfall or snowmelt when there's, and it has to be where there's an abundant supply of loose material for that heavy rainfall to reduce the friction and cause the slope to fail. These can move as fast as a few meters per second, and they're 1.5 to 2 times more dense than water alone. So they can be pretty destructive, as we've talked about. Here's what a debris flow looks like when it inundated a town. You can see it move these cars around like they were nothing. It buried stuff. It'll destroy vegetation. Yeah, pretty nasty stuff. So steep areas that are most vulnerable to debris flows usually have sparse vegetation and really intense seasonal rainfall. So you can imagine places kind of in North Central America, southern Mexico, places where it's sort of desert, but we're close to the equator. So lots of debris, not a lot of vegetation, so they get a big rainfall, and you'll get these big flows like this. They're the greatest threat to life of all the landslide hazards, and any debris flow that moves faster than 4 meters per second, then it's called a debris avalanche. Avalanches are the fastest. And in order for this to happen, for debris flows to occur, again, you have to have heavy rainfall and loose soil on a steep slope. But the two conditions that must be met is the initial period of rainfall has to saturate into the soil, and then subsequent rainfalls initiate flow. So basically you have dry material here, you get some kind of rainfall, but if you don't get enough, you're just going to add a little bit of cohesion to the debris. And so it's going to preferentially be a little bit stronger than it was when it was dry. But once it saturates and loosens the friction between the different soil grains, you get that total loss of cohesion and cohesive strength, and then the debris flow will begin, right? And as that happens, you have to remember it's picking up debris on its way down as well, right? Um, and so that body of water, that flood, will pick up debris as it moves, and so those debris flows will get more and more intense as you move down slope. Then there's this amazing picture here. This is in the San Bernardino Mountains in Southern California. And what's really crazy about this is you had some kind of big slope here, right, that failed. And this material, even though we don't have a whole lot of slope here, I mean, you can imagine, this debris moved 8 kilometers, right? And this is between 10 and 30 meters thick. So what is that? 30 to 90 feet thick. And that was all sourced from this relatively small mountain over here. And what they think happened was this stuff falls and it's thick enough and it has different sorted grains in it, so it doesn't allow a lot of air or water to move through it. When this stuff hit, similar to if you've ever played air hockey, it trapped a cushion of air underneath it, and this stuff slid this far, 8 kilometers. It's a long way. And that was just because it was riding on this kind of pocket of air that was trapped underneath the debris. I find that very fascinating, so I wanted to include it. And slides are classified by the shape of the slide surface. So if slides rotate at all, or there's a curved failure of the surface, like I said on a previous slide, we call that slump. And then if there's blocky glides or translational slides, we call that flat surface failure. And failure occurs when the force of gravity exceeds the strength of the cohesion and the materials, right? The strength of the materials, like I said. So here's kind of the geometry of a slide. So if we have discrete layers here, right, along maybe a fault surface or a joint or something like that. Maybe a portion of that breaks free and slides down this along this boundary between this sandstone and this mudstone here. So a big block will just slide down like this, leaving behind what we call a scarp at the top. So that material stays up there. This material slides down, right? We would call this the leading edge, and it's overrunning the land surface here. And so you'll get detachment along the weakening in these layers, like I said. So you need, a difference in layers for there to be a weakening. You need a place for this stuff to slide down into, and that's how we'll get this blocky slumping here. And then for rotational slumps, they tend to imagine like you take a spoon and just kind of scoop out, and like so this material is just sliding down like this, and so you're getting the slump block here, right? And there's the surface of the rupture, and the material is displacing much more at the center than it is out here on the side, so it looks rotational, right? And like I said, the slump grows headward, and it produces this kind of stair-step pattern, leaving behind scarps, similar to what we saw in the previous slide, but this is a rotational slide as opposed to a translational slide. Here's what a rotational slide looks like in the wild. So here, just based on the geometry of this particular cliff face here, you've got water eroding at the bottom here. So leaving a space for the stuff to fall down into, right? Because there's a weakening at the base. Then there's some kind of event that triggers this. And just based on the geometry of this, there's much more weight in the center than there would be out here on the sides. And so more of this stuff here in the middle would fall relative to the sides. And so you get this rotational slumping here that we see. And some things to remember about translational slides is that that's rock moving along a flat sort of planar surface, so no rotation. And again, this occurs near bedding planes. So, a difference in competency between a mudstone and a sandstone is going to leave a plane of weakness between them. And so slope failure can occur there. You can get it along foliated surfaces that have been affected by some kind of tectonic event that foliated the rock. And remember, foliation is just kind of like little tears or shears, and that can weaken the rock, so you can get failure along a foliation surface. You can also get it along faults or fractures. And the slide plane has to be slightly less inclined than the slope surface. And the factors that increase a risk of a slide like this are the slope is steepened by excavation for buildings or roads, like I said, heavy rainfall, which decreases frictional forces between the grains, and it increases the weight of the slope. And a lot of landslides, again, remember in nature, we don't just have one or the other. These are just models, right? But oftentimes, most landslides will have an element of both rotational and translational failure. So here's a rock slide, a picture of a rock slide. This is our last slide in this lecture. I kept it nice and short for you guys today. Here we have a rock slide. So a lot of them, the finer material maybe didn't make it down this far, but the bigger, rockier material may be sourced from higher up along steeper cliffs. Fell down and destroyed this road, destroyed these trucks. So this is what slides look like. And I just wanted to show you a picture because mass wasting is a big deal and something that we as geologists think often about. And so it's very important that we understand the mechanics of slope failure and mass wasting in general. And this really informs how we build our infrastructure, where we build our infrastructure, and knowing what types of materials we're building around and in is incredibly important. So that concludes a rather brief lecture on mass wasting. We do not have a lab for this go around, but there will be a few questions on the final exam or the second exam about mass wasting. So I hope you were able to take it in. And if you have any questions, just let me know. See you next time.